So here we're going to do problems 25 and 28 from section 3.5. So 25 tells us it's not a vector space. So we want to show that the set of integers, which is often indicated with just a fancy z here, is not a vector space by identifying at least one vector space property that fails. And so if you look at our list of properties that must work, so we would need things like closure. So the way we always check closure is if, say, A and B are both in this set, we might show that if we multiply C times A plus D times B, see that might not be in this set. If we could do that, we would be able to show it's not a closed set. We can also look at the other properties. Other properties there are things like, is there a zero element? Well, sure there is, right? So 0 being an integer, some integer plus 0 is equal to that integer. So there is a 0 element, so that's not an issue. We have all sorts of properties about multiplication. So the biggest thing that you're going to look at here is one of two ways you could do it. So in the way we've been defining vector spaces, we've been allowing C and D to be members of the reals. Right? So C and D are real numbers. So this would be simple enough if I just let C equal 1/2, and D equals 0, and maybe A is 5 and B is whatever number you want, 6. If we did that, A and B are integers, right? But if I multiply it by a half of A is 2.5. So this CA plus DB thing, this closure property, that's equal to 2.5, which is not an element of the integers. So this is not closed. So you can get a counterexample to those closure properties there. Pretty easy. So that's using the over-the-top one. It'd be maybe even simpler if you just looked at property 2 from the closure properties and just multiply by some different value. So we could have just done property 2, which would have been just considering some constant times an element of our space. So there's a counterexample. So it's not closed. For number 28, though, let's look at that problem. We have to do much more. So 28 asks us to verify that something is, in fact, a vector space. So what are we talking about here? So we're talking about the space of all continuous functions defined on the interval from -infinity to infinity. So we want to verify or justify with results from algebra or calculus, whichever one you choose, that the continuous functions on the real line form a vector space. So what might be helpful is to think about, well, what are our properties? So we can say, well, let's assume F, G, and we'll call it H, are all members of this continuous functions from -infinity to infinity. So we know a few things. So we know if we add two continuous functions, the result is still continuous. So this F plus G is still a member of our space. We know if you multiply a continuous function by a constant, so if you want to, you can call it, a function of t, or I guess a function of x, whatever you are comfortable with. That is still a continuous function. So if it's a 0, that's continuous. You're not going to get a jump by multiplying by a constant. So that's still in our space, continuous functions from -infinity to infinity. The third property, we're asked to verify that there's a 0. So the function, we could just define a function as 0, right? Just a constant function of 0. So then, any function plus that 0 function is just that original function. So there's a 0 element, so an additive identity. The fourth property for vector spaces is that for every vector there is a negative, right? And so if you have some continuous function, so saying f, g, and h are continuous, well, if it's continuous, then the negative version of it is also continuous. So, so we're still the fourth property is also true. Notice I'm not exactly proving these because these are results we have from calculus and algebra 2. Is it associative? Well, yeah. So when you talk about adding functions, f plus g plus h is the same as f plus g plus h. That's true for continuous functions as well. So that associative property is still true. Is it commutative? Yeah, it's definitely commutative. So we can always say that if you have two continuous functions, f and g, you could write it as g plus f. And notice I'm being a little loose with my notation here, and that sometimes I'm including function notation that includes the argument, but all these are assumed to be function f, function g, as I'm writing. I'm doing sort of a quick shorthand form here. The seventh property is there a multiplicative identity? Well, yeah, we can multiply 1, right? Just the number 1 times the function is just, now here I'll say 1 times a function of x, that's just that function. So that's true as well. The eighth property is it distributive? Yeah, you can definitely, I'm just more or less here writing out results that we do already have. That's also true from just our work with functions. Also, you can distribute it, the function through there, so c plus d times the function of x. I could write that as c times the function of x plus d times the function of x. Notice I could use an example, let f and g be whatever, a polynomial, sine function, whatever you want, but an example is not enough for a proof. And it's associative. It doesn't matter if I multiplied the function times d first or multiplied c times d first. So all 10 of those properties apply to functions that are continuous on the real number line from negative infinity to infinity. And so all of these work, and therefore it is a vector space.